Tonight, this recording is here simply to keep you gentle company while you drift towards sleep. You don't have to remember anything, you don't have to follow every idea, and you definitely don't have to stay until the end if sleep arrives earlier. All that matters right now is to get comfortable. Feel the support beneath your body and allow your thoughts to slow down while the words move past like a quiet, slow-moving river. If you like, you can softly notice your breathing. Not changing it, not forcing it, just feeling the natural rise and fall of each inhale and exhale. With every breath out, you can let a bit of tension melt from your shoulders, your neck, the muscles of your face, as if you're exhaling the remains of the day. You are not competing with anything now, not preparing for anything. This time belongs only to rest. You might imagine all the concerns of the day gently staying behind you, like the lights of a distant city slowly slipping below the horizon. Around you, it becomes darker and quieter, and above you, a calm night sky opens up, full of stars and galaxies. Their light has traveled for millions and billions of years just to be softly present in this moment while you lie here, safe, gradually drifting into sleep. I'm glad you found your way here, because tonight we'll be exploring some of the greatest mysteries in all of physics. Quiet questions that drift at the edge of our understanding and tug gently at the fabric of what we think we know. At this very moment, the night sky is full of countless stars, galaxies, and untold wonders. Their light has traveled for millions, even billions of years, crossing unimaginable distances just to reach you in this sleepy moment. It's humbling when you think about it. For all our technology, all our theories and observations, we still don't know what most of the universe is made of. We've mapped the galaxies, we've measured the age of the cosmos, we've even traced the whisper of the Big Bang. But beyond all of that, something else remains. Something vast, invisible, powerful, and largely unknown. Dark matter, dark energy, forces and substances that shape the cosmos on the largest scales, bending galaxies, accelerating expansion, and rewriting the boundaries of what physics can explain. We can see their effects, we know they're there, but we don't know what they are. And that's where we begin. All across the universe, galaxies spin, vast wheels of stars and gas whirling through space. But when astrophysicists measured how fast they rotate, something didn't add up. The stars at the edges were moving far too quickly. Based on the gravity from visible matter alone, stars, planets, gas, those outer stars should have been flung into deep space. Instead, they stayed in orbit as if held by some invisible glue. That glue, it seems, is dark matter. We call it dark not because it's sinister, but because it doesn't emit, absorb, or reflect light. It's invisible to our eyes, to our telescopes, to every known form of electromagnetic detection. And yet we know it's there, not by seeing it, but by seeing what it does. It tugs on galaxies, bends light around clusters, and sculpts the shape of the universe on its grandest scales. It outweighs all the normal matter we can see by a factor of 5. In a very real sense, dark matter dominates the cosmos. We just don't know what it is. The story begins in the 1930s with the Swiss astronomer Fritz Zwicky. While studying the Coma Cluster, a group of galaxies bound together, he noticed the galaxies were moving so fast they should have flown apart, but they hadn't. He proposed that some unseen mass, which he called dark matter, must be holding the cluster together. His ideas were dismissed for decades, set aside like a strange footnote. But in the 1970s, Vera Rubin and Kent Ford observed the rotation curves of individual galaxies and confirmed the same strange pattern. Outer stars were moving far too fast. The gravitational pull of visible matter alone couldn't explain it. Since then, galaxy after galaxy has shown the same signature: flat rotation curves refusing to fall off with distance as Newtonian physics would predict. It's as if each galaxy is embedded in a vast, invisible halo, a cocoon of mass we cannot see but must account for. Even when galaxies collide, the dark matter doesn't behave like gas or stars. It passes through undisturbed, like a ghost. The Bullet Cluster, a pair of merging galaxy clusters, provided one of the most striking pieces of evidence. Using gravitational lensing, astronomers mapped where the mass truly was, and it didn't match the glowing clouds of visible matter. It matched the dark. Gravitational lensing, the bending of light by mass, has become one of our most powerful tools for detecting dark matter indirectly. When light from a distant galaxy passes through a cluster on its way to Earth, the cluster acts like a lens, warping the image. By analyzing these distortions, we can map the mass distribution in the foreground, even if we can't see it. Again and again, these maps reveal more mass than we can explain with stars and gas alone. And yet, despite this overwhelming indirect evidence, dark matter continues to evade direct detection. We can describe its effects with precision. We can calculate how much of it there must be. Pause 3 seconds. But the particles themselves, the fundamental stuff of dark matter, remain a mystery. Pause 3 seconds. They do not seem to interact with ordinary matter through any force except gravity, and even that only weakly. Pause 3 seconds. So what could it be? Pause 3 seconds. Over the past few decades, physicists have proposed a number of candidate particles to explain dark matter. Pause 3 seconds. One of the earliest and most studied possibilities is the WIMP, the weakly interacting massive particle. WIMPs are hypothetical particles that interact via the weak nuclear force, but not the electromagnetic force, which would explain their invisibility. Their predicted mass and properties arise naturally in many extensions of the Standard Model, including supersymmetry. For years, WIMPs were the leading contender. Entire underground laboratories were built to catch them, massive detectors shielded from cosmic rays and background noise, waiting for a rare collision. But none came. As experiment after experiment returned null results, attention turned to other candidates. One is the axion, a lightweight, ghostly particle first proposed to solve a problem in quantum chromodynamics, the theory of the strong force. Axions are incredibly light, but could exist in such enormous quantities that they add up to a major source of mass. Specialized detectors are now tuning in to the narrow frequencies axions might produce as they convert into photons in a magnetic field. Other ideas go further afield. Sterile neutrinos, hidden sector particles, even primordial black holes. Some researchers suggest dark matter might not be a new kind of particle at all, but instead a sign that our understanding of gravity needs to be adjusted, an approach known as modified Newtonian dynamics. And yet, none of these have yet answered the riddle. What dark matter is made of remains uncertain. But what it does, how it shapes the universe, is better understood. In fact, without dark matter, the cosmos as we know it couldn't exist. In the early universe, shortly after the Big Bang, ordinary matter was too hot and energetic to collapse into structures. It interacted strongly with light, which kept it from clumping. But dark matter, unaffected by radiation, could begin to form dense regions even in the earliest moments of time. These became the gravitational wells into which ordinary matter would eventually fall. In this way, dark matter served as scaffolding. Pause. Tiny fluctuations in the density of dark matter provided the seeds around which galaxies and clusters could grow. Simulations of cosmic evolution show this vividly. When dark matter is included, the resulting web of large-scale structure, filamentary networks of galaxies and voids, matches what we see in the sky. Without dark matter, the universe looks nothing like it does. There would be no galaxies, no clusters, no stars, and very likely no us. There would be no us. It's not just about formation either. Dark matter still plays an active role in holding galaxies together. Its presence explains the stability of spiral galaxies, the shapes of galaxy clusters, and the patterns we see in the cosmic microwave background. These fingerprints, subtle ripples in ancient light, match the predictions of a universe where dark matter outweighs normal matter 5 to 1. It's not just a patch for missing mass, it's woven into the very blueprint of cosmic evolution. And yet, we still haven't found it. Not directly, not unmistakably. The scaffolding is there, holding up the cosmos, but the beams remain invisible. So why can't we find it? Despite decades of effort, not a single confirmed dark matter particle has been observed in a laboratory. The problem is one of interaction. Ordinary matter reveals itself in countless ways through charge, light, heat, friction. But dark matter seems to interact only through gravity and perhaps the weak nuclear force. That makes it extraordinarily hard to catch. Most particles pass through our bodies by the trillions every second, unnoticed. Dark matter does the same, but without leaving a trace. Experiments designed to detect WIMPs, for example, rely on a dark matter particle occasionally striking an atomic nucleus and transferring a tiny amount of energy. These detectors are buried deep underground in old mines, mountain caverns, shielded by rock to block background noise. But even with extreme sensitivity and years of observation, the results remain frustratingly empty. Other methods, like looking for dark matter annihilation signals in space, or its production in particle accelerators like the Large Hadron Collider, have also returned no clear evidence. It's possible we've been looking in the wrong place or for the wrong thing. Part of the difficulty may lie in our assumptions. Many early searches were guided by elegant theories like supersymmetry, which predicted certain kinds of particles in certain mass ranges. As those are ruled out, the parameter space widens. Dark matter could be lighter, heavier, colder, more diffuse, or something stranger altogether. It may not exist in the form of particles at all. It may behave like a field. It may interact with itself in ways we haven't imagined. Or, more radically, perhaps our understanding of gravity breaks down on large scales. Each path leads deeper into uncharted physics. And that's what makes dark matter so profound. This isn't just a case of a missing piece. It's a sign that our entire picture of matter, of what the universe is made of, may be incomplete. The standard model of particle physics is one of the most successful theories in science, but it doesn't include dark matter. Whatever dark matter is, it lies outside our current framework. Which means it isn't just a problem for cosmology. It's a doorway to new physics. If we can understand dark matter, we may open the door to entire realms of particles and forces we've never seen. Our current view of matter is based on a few familiar building blocks: protons, neutrons, electrons, and their interactions through four known forces. But nature may be far more diverse. Dark matter could be the tip of an unseen sector of physics, a shadow world with its own particles, its own symmetries, its own dynamics. This possibility reshapes how we think about the cosmos. The matter we see, the stars, the gas, the planets, even ourselves, might be just a thin glaze on the surface of a much deeper reality. A kind of luminous icing floating on a dark ocean. We have spent centuries studying the visible universe. But if dark matter truly dominates it, then most of the universe is still invisible, not just in appearance, but in essence. And that's humbling. It suggests that what we call normal matter may not be normal at all, just familiar. In recent years, the search for dark matter has grown more creative and more urgent. New generations of detectors are pushing sensitivity to unprecedented levels, probing weaker interactions and lower masses than ever before. Some now target ultra-light dark matter candidates using resonant cavities, superconducting circuits, or even vibrating crystals. Others look to the skies. The Fermi Gamma Ray Space Telescope scans the galactic center for annihilation signals, while gravitational wave detectors explore whether dark matter could consist of tiny black holes from the early universe. Still others turn to quantum technologies, using cold atoms, interferometers, or nanoscale sensors to detect the faintest of tugs. But with every new approach comes more complexity and more questions. What if dark matter isn't just one thing, but many? Could it consist of multiple components like ordinary matter does? Might it interact with itself, forming invisible structures or dissipating energy in ways we haven't yet detected? And perhaps most troubling, what if dark matter doesn't exist at all? What if the evidence we see is pointing not to missing mass, but to a misunderstanding of gravity? Modified gravity theories like MOND or emergent gravity offer alternative explanations, though they remain controversial and incomplete. The truth is, we don't yet know. And that uncertainty, while frustrating, is also what makes this search so powerful. Because to solve the dark matter mystery is to confront the boundaries of knowledge itself. We're no longer just weighing galaxies or mapping halos. We're testing the limits of our theories, our tools, and our understanding of what the universe is made of. Pause. And in doing so, we're reminded that the cosmos still holds secrets, vast, invisible, and waiting. It might be hard to believe, but the story gets even stranger. In the late 1990s, two independent teams of astronomers were studying distant supernovae, brilliant stellar explosions that serve as cosmic milestones. They were trying to measure how quickly the universe's expansion was slowing down. Gravity, after all, pulls things together. So the assumption was that over time, the expansion from the Big Bang would be decelerating. But when the results came in, the astronomers were stunned. The supernovae were dimmer than expected, farther away than they should have been. The universe wasn't slowing down, it was speeding up. This discovery that cosmic expansion is accelerating shook the foundations of cosmology. Something was pushing space itself to stretch faster and faster, defying gravity's pull. But what could it be? The simplest explanation, first proposed by Einstein and then discarded, was the cosmological constant, a kind of intrinsic energy of space. But even that idea raised thorny questions. If space contains energy, how much? Why that amount? And where does it come from? Lacking answers, physicists gave the phenomenon a new name: dark energy. But like dark matter, it remains unseen, known only through its effects. At first glance, dark energy and the cosmological constant might sound like two names for the same thing, but there's an important difference. The cosmological constant, denoted by the Greek letter lambda, is a fixed value, a uniform energy density that fills space evenly, never changing over time. It was introduced by Einstein in 1917 as a fudge factor to keep the universe static, later discarded when the expansion of the universe was discovered. But now, in light of the accelerating cosmos, it's returned not as a mistake, but as a serious contender. Dark energy, by contrast, is a broader term. It encompasses the cosmological constant, but also includes more exotic possibilities. What if this energy isn't constant? What if it evolves over time? These alternatives fall under the umbrella of dynamic dark energy, with one of the most studied models known as quintessence. In these theories, dark energy is a field that varies across time and space, more like the scalar fields used in inflationary cosmology. Depending on its behavior, it could lead the universe to expand forever, to rip apart, or to slow down again in some future epoch. But no matter the model, the effect is the same. Dark energy dominates the large-scale behavior of the universe. About 68% of the universe's total energy content appears to be in the form of dark energy. It doesn't clump like matter, and it doesn't dilute as space expands. Instead, it exerts a kind of negative pressure, a repulsive force woven into the very fabric of space-time. This subtle yet persistent push affects the universe's expansion rate, the growth of cosmic structures, and even the ultimate destiny of everything we know. Over billions of years, dark energy has reshaped the cosmos. In the early universe, matter, both normal and dark, was the dominant force. It pulled together clouds of gas, forged galaxies, and carved the great cosmic web. But as the universe expanded, the density of matter decreased, while the influence of dark energy remained constant or even grew. At a certain point, around 5 billion years ago, dark energy overtook matter as the driving force of cosmic evolution. Since then, galaxies have drifted farther apart, the expansion has accelerated, and the structures of the universe have begun to freeze into place. This acceleration means that distant galaxies are now receding from us at ever-increasing speeds. Eventually, regions of space beyond a certain distance will move away faster than light can bridge the gap. Those galaxies will fade from view, becoming forever unreachable. Cosmic isolation will deepen. In trillions of years, the night sky could grow dark again, not because stars have gone out, but because the universe has expanded so much that light can no longer cross the void. The future may hold not just silence, but solitude on a cosmic scale. And yet, this is only one possible fate based on what we think dark energy might be. The truth is, we still don't know. Is it truly constant? Is it changing? Is it even real, or a sign that our understanding of gravity needs revision? Just as with dark matter, these aren't questions of idle speculation. They cut to the heart of physics, of what space and time themselves are made of. To study something as elusive as dark energy, astronomers rely on the universe itself as a laboratory. Supernovae, the massive explosions of dying stars, are one of the most powerful tools. These stellar explosions occur in binary systems when a white dwarf accretes matter from a companion star until it reaches a critical mass and detonates. Because they occur under similar conditions, they have nearly uniform intrinsic brightness. This makes them standard candles, objects whose distances can be estimated by comparing their known luminosity with how bright they appear. By measuring the redshift of these supernovae, how much their light has been stretched by the expansion of space, astronomers can reconstruct how the universe has expanded over time. That's how the acceleration was first discovered. And ever since, these stellar beacons have continued to trace the cosmic expansion, providing key evidence for dark energy's influence. But supernovae are not the only line of evidence. The cosmic microwave background, the faint afterglow of the Big Bang, provides a snapshot of the universe as it was just 380,000 years after its birth. Embedded in this light are tiny fluctuations in temperature which encode information about the geometry and contents of the cosmos. When dark energy is included in the models, the positions and amplitudes of these fluctuations align beautifully with what we observe. Without it, the picture doesn't fit. Other probes include baryon acoustic oscillations, subtle ripples in the distribution of galaxies, and weak gravitational lensing, where the shapes of distant galaxies are slightly distorted by intervening mass. Together, these methods converge on the same conclusion: the expansion of the universe is accelerating. Dark energy is real, or something that mimics it is. But the what remains unsolved. Quantum field theory tells us that even a perfect vacuum isn't truly empty. Instead, it seethes with temporary particle-antiparticle pairs popping in and out of existence. These quantum fluctuations give rise to a non-zero energy density. And in theory, this vacuum energy should behave exactly like the cosmological constant. But when physicists try to calculate how much energy this vacuum should contain, the numbers go haywire. The result is off by a staggering factor, somewhere between 1012, 1012, and 1038, 1038 times larger than what we actually observe. This discrepancy is often called the worst theoretical prediction in physics. Why is the vacuum energy so small? Why is it not zero? And why is it roughly the same order of magnitude as the matter density of the universe right now? These questions have no satisfying answers. Some physicists suspect an unknown symmetry cancels most of the vacuum energy. Others invoke the anthropic principle, the idea that we observe this value because only universes with similar values can support life. But these are not fully predictive explanations. They are placeholders for deeper insights still to come. In response to this crisis, other theories have emerged. Quintessence models posit a dynamic field, similar in spirit to the Higgs field, that slowly evolves over time. Unlike a constant, its influence can grow or fade depending on the properties of the field. This opens the door to a wider range of cosmic fates, but also makes the physics harder to constrain. The space of possibilities becomes enormous, and without firm observational handles, many models remain speculative. Still, some of them leave signatures, subtle changes in the equation of state of dark energy, or variations in its density with redshift. Future surveys hope to test these. One of the most striking consequences of dark energy is its effect on the geometry of space-time itself. In general relativity, the distribution of energy and matter determines the curvature of space. In a universe dominated by matter, the curvature depends on the total density. If it's high, space curves inward, a closed universe. If it's low, it curves outward, an open universe. But dark energy, particularly in the form of a cosmological constant, changes that relationship. It doesn't clump like matter or dilute as the universe expands. Instead, it acts as a constant outward pressure, stretching space and accelerating time's passage from one cosmic epoch to the next. Observations of the cosmic microwave background, large-scale galaxy clustering, and lensing patterns suggest that the universe is remarkably flat on large scales, precisely what you'd expect in a universe balanced between matter and dark energy. But it's a delicate balance. Slight changes in the amount or behavior of dark energy would tip the geometry, altering how light travels, how structures grow, and how the universe unfolds. This expansion isn't just a gentle swelling. It rewrites the ultimate destiny of the cosmos. If dark energy is truly constant, then galaxies will drift ever farther apart, stars will burn out, and the universe will grow colder and emptier, a future often called the Big Freeze. But if dark energy strengthens over time, as in some phantom energy models, it could lead to a big rip where the expansion becomes so extreme that even atoms are torn apart. Alternatively, if dark energy decays or reverses, the cosmos could eventually collapse in a big crunch. The shape of tomorrow hinges entirely on the physics of dark energy. Pause 3 seconds. And right now, we are only guessing. To close the gap between theory and reality, physicists and astronomers have turned to a new generation of instruments and surveys. The Euclid Space Telescope, launched by the European Space Agency, is mapping billions of galaxies to chart the expansion history of the universe and the influence of dark energy over cosmic time. The Vera C. Rubin Observatory in Chile, with its 10-year legacy survey of space and time, will observe the visible sky every few nights, building an unprecedented data set of transient events and gravitational lensing effects. NASA's upcoming Nancy Grace Roman Space Telescope will complement these efforts, using wide-field infrared imaging to detect subtle signatures of cosmic acceleration. Each of these missions is designed not just to confirm the presence of dark energy, but to constrain its properties, to test whether it behaves like a cosmological constant or something more complex. These experiments may help determine whether dark energy evolves over time, whether it clumps in unexpected ways, or whether it connects with deeper layers of particle physics and field theory still waiting to be uncovered. But for now, many questions remain wide open. What is the true nature of dark energy? Why did it begin to dominate the universe's expansion only recently in cosmic history? Is it related to quantum fields, vacuum energy, or something stranger? Does it point to extra dimensions, multiverse models, or undiscovered symmetries in the laws of physics? Or is it a hint that general relativity itself, the very structure of space-time, needs revision? In many ways, dark energy is not just a phenomenon. It is a boundary, a vast expanding edge to our understanding. We know it's there. Pause. We feel its influence in the motion of galaxies and the dimming of distant stars. But its cause, its meaning, its place in the puzzle of the cosmos, those remain hidden. Black holes are among the most mysterious and extreme objects in the universe. They begin as a consequence of gravity pushed to its limit. When a massive star exhausts its nuclear fuel, nothing remains to resist the inward pull of its own weight. If the collapse is complete, the core compresses beyond all known matter states, forming a singularity, a point of effectively infinite density where space-time itself breaks down. Around this singularity forms the event horizon, a boundary from which nothing, not even light, can escape. It is not a solid surface, but a threshold. Cross it and return becomes impossible. At the heart of a black hole, our familiar laws of physics falter. General relativity, which describes gravity and the curvature of space-time, predicts the formation of the singularity, but also signals its own failure there. Infinite density, infinite curvature, these are signs that a more fundamental theory is needed. Quantum mechanics, which governs the behavior of particles on the smallest scales, has no clear answer for what happens at the center of a black hole. The event horizon shields that mystery from view, locking it behind a veil that no signal can pierce. We know the black hole exists, but not what truly lies within. For decades, it was thought that black holes were simple, defined entirely by their mass, charge, and spin. They could swallow stars, gas, even light itself, but they gave nothing back, just a dark gravitational footprint. Then, in the 1970s, Stephen Hawking changed everything. Combining ideas from quantum field theory and general relativity, he showed that black holes aren't completely black. Instead, they emit a faint glow of particles, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where pairs of virtual particles pop into existence. One falls in, the other escapes. From far away, it looks as if the black hole is slowly evaporating. This was a revolutionary insight, but it led to a deep problem. As the black hole emits Hawking radiation, it loses mass. Over time, if no new matter falls in, it shrinks. Eventually, it may evaporate entirely, vanishing into a final burst of radiation. But here's the paradox. What happens to the information about everything the black hole once consumed? In quantum mechanics, information is never truly lost. The evolution of a closed system is reversible. The wave function evolves smoothly according to the Schrödinger equation. But in Hawking's picture, the radiation is completely thermal. It carries no imprint of the black hole's internal contents. If the black hole disappears, and the information is not encoded in the radiation, then it is lost forever. This violates one of the core principles of quantum theory. It sparked what has become one of the most profound puzzles in theoretical physics, the black hole information paradox. How can we reconcile Hawking radiation, which seems to destroy information, with a universe that at its most fundamental level should conserve it? The stakes are enormous. If information can be lost in black holes, then quantum mechanics itself may be incomplete. If it cannot, then something about our understanding of black holes or space-time must change. And the paradox only deepens the more closely we look. One of the most surprising developments in black hole physics was the realization that black holes have entropy. In classical physics, entropy is a measure of disorder, or more precisely, of the number of microscopic configurations that correspond to a given macroscopic state. Pause. A glass of water has entropy. A star has entropy. But a black hole seemed too simple. Defined only by mass, spin, and charge, it appeared to lack the internal degrees of freedom that give rise to entropy. And yet, Hawking's work, along with that of Jacob Bekenstein, revealed that black holes must have entropy proportional to the surface area of their event horizon, not their volume. This was a profound shift. It suggested that information content in a black hole scales with its boundary, not what's inside, but what lies on the edge. Bekenstein's formula, later refined by Hawking, shows that the entropy of a black hole is proportional to the area of the event horizon divided by the Planck length squared. That means the entropy of a black hole is immense, far greater than that of ordinary matter of the same mass. This connection between area and entropy led to the holographic principle, the idea that the fundamental description of a region of space may be encoded on its boundary. Pause 3 seconds. But understanding exactly what those microscopic states are and how they store information requires a theory of quantum gravity. Pause 3 seconds. General relativity describes black holes as smooth geometrical objects, while quantum mechanics demands a granular, probabilistic structure. Pause. Reconciling the two requires a deeper framework, one that can describe space, time, and information on the smallest possible scales. Several approaches have tried to bridge the gap. In string theory, black holes can be modeled using collections of strings and branes whose quantum configurations match the expected entropy. Loop quantum gravity, another candidate theory, describes space-time as a network of discrete loops, which might account for black hole microstates in a different way. But no theory has yet emerged as definitive, and the paradox remains. One proposed resolution is that the information is somehow encoded in the Hawking radiation after all, that it's not truly thermal, but subtly entangled with the interior of the black hole. As the black hole evaporates, quantum correlations might allow the information to escape in a scrambled but recoverable form. This would preserve unitarity, the rule that quantum evolution is reversible, and save the foundations of quantum theory. But it raises new questions. How does the information get out? Through what mechanism? And if it escapes, does that violate the idea that nothing can travel faster than light? To address this, some physicists proposed a dramatic possibility: the firewall hypothesis. According to this idea, the smooth horizon of a black hole is an illusion. Instead, an infalling observer would encounter a wall of high-energy radiation, a firewall, at the horizon, where quantum entanglement breaks down. This would allow information to escape, but at the cost of violating another cherished principle of physics, the equivalence principle, which says that free fall through empty space should feel smooth and uneventful. The firewall proposal preserves unitarity, but only by sacrificing general relativity's core symmetry. It's a bold move, and one that remains highly controversial. Some researchers view firewalls as a sign that we've reached the limits of our current framework. Others see them as an artifact of overly strict assumptions. But all agree that the resolution to the black hole information paradox will likely involve new physics, perhaps even a new understanding of what space, time, and information really are. Despite their mystery, or perhaps because of it, black holes have become invaluable tools for physicists. They are not just astrophysical curiosities. They are crucibles where the known laws of nature are pushed to their breaking point. In the intense gravity near a black hole's event horizon, time slows, space stretches, and tidal forces grow strong enough to rip apart atoms. These are the most extreme conditions the universe naturally provides, conditions that cannot be replicated in any laboratory on Earth. Studying black holes allows us to test general relativity in its most extreme regime and to probe the edge of quantum physics, where our current understanding begins to crack. In that way, every black hole is a natural experiment, a cosmic laboratory in which space and time are distorted beyond ordinary recognition. We can't peer into the singularity itself, but we can observe the behavior of matter and light near the event horizon. We can measure the orbits of stars around black holes, as has been done at the center of the Milky Way, where a supermassive black hole named Sagittarius A star anchors our galaxy. We can study the accretion disks of hot gas swirling around black holes, emitting X-rays and high-energy radiation. And now, with the advent of gravitational wave astronomy, we can detect the ripples in space-time caused by the collisions and mergers of black holes, signals that carry information directly from the most violent events in the universe. These observations provide essential data points, but the deeper conflict remains. Black holes sit at the intersection of two great but incompatible theories. Quantum mechanics describes the probabilistic behavior of particles and fields on the smallest scales and has been tested with exquisite precision. General relativity describes gravity as the curvature of spacetime and has passed every observational test in the macroscopic world. But when we try to combine the two, especially in extreme environments like black holes, contradictions arise. The information paradox is one example. Singularities are another. And the failure to describe what happens inside a black hole shows that neither theory on its own is complete. This incompatibility has driven the search for a theory of quantum gravity, a unified framework that can describe all forces, all particles, and all scales. String theory and loop quantum gravity are leading candidates, but they remain mathematically complex and difficult to test. Holography, inspired by black hole entropy, offers another promising path. According to the ADS/CFT correspondence, a duality proposed in string theory, a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity on its lower dimensional boundary. In this picture, a black hole in one universe corresponds to a quantum system in another, where information is preserved. This holographic principle has become a powerful tool for studying quantum gravity in highly symmetric spacetimes. Even if this specific duality doesn't apply to our universe directly, it suggests that space and time may be emergent, not fundamental ingredients of reality, but macroscopic effects that arise from deeper quantum structures. In such a view, black holes might not be puzzles within spacetime, but clues to how spacetime itself comes into being. And so, black holes continue to illuminate the deepest fault lines in physics. They demand that we confront the paradoxes we'd prefer to ignore. They blur the lines between known and unknown, between the classical and the quantum. And they hint, perhaps more clearly than any other object, that the universe is governed by principles we have not yet fully grasped. At the forefront of black hole research, new ideas continue to challenge our assumptions and sometimes our imaginations. One avenue explores quantum entanglement as a possible bridge between the interior and exterior of a black hole. The so-called ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, wormholes, and quantum entanglement may be two sides of the same coin. In this picture, particles that are entangled may be connected by tiny wormholes, and a black hole's interior could be related to the entangled structure of the Hawking radiation it emits. It's an elegant idea, though still speculative, and it hints that space-time geometry and quantum information may be more deeply intertwined than we've realized. Elsewhere, physicists are revisiting the notion of complementarity, the idea that different observers may have different but equally valid descriptions of the same physical system. From outside, a black hole looks like a hot, radiating object with no visible interior. From the perspective of someone falling in, the event horizon is smooth and nothing unusual happens upon crossing it. These views seem contradictory, but some theories suggest they can coexist, not through illusion, but through a deeper, unified description. What unites all these efforts is a shared recognition. Black holes are more than endpoints of gravitational collapse. They are crucibles of fundamental physics, places where gravity, quantum mechanics, thermodynamics, and information theory all meet. By studying them, we hope not only to understand these strange objects themselves, but to glimpse the deeper laws that govern the universe. At the edge of all these questions, dark matter, dark energy, black holes, quantum gravity, lies a simple truth. Our understanding of the universe is still incomplete. We have equations that work beautifully in many situations, experiments that confirm them to astonishing precision, and observations that map the cosmos across billions of light years. And yet, the most fundamental components of reality, the invisible mass that holds galaxies together, the mysterious energy that drives cosmic acceleration, the true nature of space-time inside a black hole, remain elusive. For some, this uncertainty is unsettling, for we like to think of science as a finished book, its chapters neatly written and bound. But in truth, science is more like a lantern carried through a vast, dark landscape. The light illuminates what is near, revealing patterns and pathways. But beyond the glow, mystery always remains. Each discovery pushes the boundary outward a little farther, only to reveal new questions beyond. In that sense, the dark components of the universe are not just gaps in our knowledge. They are invitations to look deeper, to build better instruments, to imagine new theories, and to accept that the cosmos is richer and stranger than our current ideas. The fact that most of the universe is dark in one way or another, unseen yet influential, suggests that what feels familiar, stars, planets, people, is only a thin slice of a much larger reality. As you lie here, listening, you don't have to solve any of these puzzles. You don't need to decide whether dark energy is a cosmological constant or a dynamic field, whether dark matter is a particle or a modification of gravity, whether black holes erase information or encode it in subtle ways. All of these questions can stay out there, drifting among the galaxies, while you stay right here, anchored in your own quiet corner of the universe. You might imagine the vast structures we've talked about, the cosmic web of galaxies, the invisible halos of dark matter, the expanding fabric of space, the deep wells of black holes. Not disappearing, just receding into the distance, like constellations fading behind soft clouds. The scale of the universe gently contracts, layer by layer, until you're no longer thinking about clusters and filaments and horizons, but simply about this room, this bed, this moment. Notice again the feeling of the surface beneath you, the way it supports your weight without effort, the quiet heaviness of your body, like a small, calm planet resting in its orbit. You don't have to hold yourself up. Gravity is doing that for you. You can let your muscles soften just a little more, around your eyes, your jaw, your shoulders. If any thoughts about the day drift in, things you said, things you did, things you still need to do, you can imagine them as tiny satellites circling far above you. You don't have to chase them or push them away. You can let them continue in their orbits while you stay at the center, still and quiet. Whenever you notice you followed one of those thoughts, you can gently come back to something simple, like the feeling of your breath or the contact of the blanket against your skin. Just as galaxies move through the universe without needing your attention, your thoughts can move through your mind without needing your involvement. You can watch them from a distance, or you can let them fade completely into the background. There is nothing urgent to understand right now, nothing that demands analysis or decision. The universe will continue doing what it does, expanding, evolving, hiding its deepest secrets, whether you are awake or asleep. You, meanwhile, are allowed to rest, to become, for a little while, just a quiet observer who doesn't need to observe. A small, warm presence in a vast, dark cosmos, held gently by gravity, wrapped in air and silence. With each breath, your body knows a little more how to let go. Muscles loosen, thoughts blur at the edges, and the boundary between waking and sleep grows softer. If sleep comes slowly, that's all right. You don't have to force it or hurry it along. Just as light from distant galaxies takes its time crossing the universe, your mind can take its time drifting into rest. You can stay exactly where you are, listening or not listening, letting the words rise and fall like gentle waves on a very quiet shore. At some point, you may stop following the sentences altogether. They might turn into fragments, then into single words, then into nothing at all. When that happens, it's perfectly fine. When that happens, it simply means that your mind has decided it no longer needs these stories tonight. It can set them down like a book and sink more deeply into the soft, wordless dark of sleep. You don't need to hold on to every term or every theory. You can let them drift by like constellations slowly moving across the sky, there and then gone from view, while you remain grounded, safe, and still. You don't have to decide which ideas to keep and which to forget. Pause 3 seconds. Your mind will do its quiet sorting on its own, setting some thoughts gently aside while it lets others drift deeper into the background. All that matters right now is the simple rhythm of your breathing and the steady support beneath your body. As you listen, you might imagine yourself lying under a wide open sky, with galaxies and clusters scattered far above, moving on timescales so long that they feel completely still. The universe can keep unfolding and evolving without your help tonight. You are allowed to be small here, to let go of all responsibilities and questions, and to rest like a quiet planet in a safe, stable orbit.